Thank you for the introduction. I am an employee of Canon Medical System USA, formerly Toshiba Medical. Deep learning has recently applied in many medical applications for segmentation. For example, there is a group in UK has demonstrated that a CNN model can provide comparable to human experts in analyzing cardiac DNA. So the goal of my work is to apply CNN for automatic segmentation of myocardial ASL. And more importantly, we want to measure model uncertainty using Monte Carlo dropout and to adapt the CNN model to the desired trade-off between false positive and false negative of the application using Tversky loss function. So myocardial ASL is a non-contrast perfusion technique that is able to quantify myocardial blood flow. It's also able to detect coronary artery disease. However, it requires typically 3 to 5 minutes manual segmentation. Different from CNA images on the top right, ASL data typically has lower SNR, lower CNR, and has lower resolution. Furthermore, SNR and CNR is varying due to heart rate variation and from patient to patient, as you can see in the label images on the left. And another consideration of quantitative cardiac imaging is partial volume effects, because myocardium is surrounded by ventricular blood pools and also epicardial fat, which has very different physical property and also spin history compared to myocardium. And model uncertainty is important for quality control during production and deployment of the model. And also it could be used to improve model via active learning, as you can see in the diagram below. This is a network we use for our work. It's basically UNet with a few modifications. First, we added the Monte Carlo dropout to estimate model uncertainty. And also we can use Tversky loss function to adapt our network to desire for positive and for negative trade-off. And training and validation data was collected from 22 subjects. And test data was from 6 unseen heart transplant patients acquired rest and during adenosine stress. This is a standard definition of Dice coefficient, where A is a predicted mask and B is a reference mask. Alternatively, we can define Dice coefficient as a function of false positive and false negative. And so as we can see in this definition, false positive and false negative are weighted equally in Dice coefficient. In order to adapt a network, we use a Tversky loss function, in which there is a hyperparameter beta that we can change during training so that we can adapt the network to the desired false positive and false negative. And as we can see, if beta equals 0.5, Tversky loss function is exactly the same as Dice loss function. And this is the result of our study. Overall, over the test sets, we achieved a 0.9 Dice accuracy. And on the right are the myocardial perfusion map, a quantitative map that we care about. The automatic segmentation has very similar performance to the manual segmentation. And overall quantitative assessment, we can see that the MBF measure from automatic segmentation is highly correlated with that measure from reference manual segmentation. This is the result for uncertainty measure. On the x-axis is the uncertainty measure using Monte Carlo dropout, given the manual segmentation. However, during production, manual segmentation may not be available. So on the y-axis is the Monte Carlo dropout to estimate the model uncertainty without the knowledge of manual segmentation. And as we can see in this correlation plot, 2 ways of measure uncertainty are in good agreement. And let's take a look on an example in the test case where the uncertainty is low. You can see that automatic segmentation has a good agreement with manual segmentation. Another example with high uncertainty, we can see there is a discrepancy between automatic segmentation and manual segmentation. Furthermore, with the uncertainty map, we can have the spatial information where the model is most uncertain. In this case, we use 1,000 multicolor trial for an example, but for the practical application, do we really need 1,000? This is plot show the inference time as a function of number of multicolor trial. And we can see that with the lower number of multicolor trial, we have significantly less time. And with variety of multicolor trial, the uncertainty estimation is very similar. And let's say if we take around 128 multicolor trial, it only takes around 1.5 seconds per sample. So it's a trade-off for practical purposes. We can use some smaller number of multicolor trial with reasonably good uncertainty estimation. And this showing the effect of partial volume effects to the quantification. In the middle is the original manual segmentation. Thin mask is simply produced by removing one pixel from both sides. And thick mask is simply we added one pixel from both sides of the original mask. And as we can see, thin mask and thick mask had very similar dice coefficient. However, the false positive and false negative rates of these two masks are completely opposite. And this is a consequence to the quantitative measure. Thin mask doesn't produce any significant bias to the quantification. However, the thick mask produce significant overestimation because of partial volume effect. And this is a result from our study to demonstrate the adaptability of the technique to the desired false positive and false negative trade-off. So if we take a thick mask, which is an extreme case, there is no false negative. And then the false positive is around 400 pixels per image for entire test set. And if we take the thin mask, another extreme on the other side, we have no false positive, but false negative is 300 pixels per image on average. And this is a network trained with the binary cross entropy. And this is the false positive and false negative of that loss function. And the network trained with dice coefficient, this is the false positive and false negative of the dice coefficient. And we can see they are very similar. And then the circle are the false positive and false negative of the network trained with the Tversky loss function. And for cardiac imaging, we may prefer to use beta bigger than 0.5. So that is a conclusion of this slide. And in conclusion, this study demonstrates the feasibility of using CNN model for the data with very low SNR and also varying SNR and CNR. And more importantly, we can quantify model uncertainty and to adapt our network to the desired false positive and false negative trade-off. And that can be applied for many quantitative cardiac imaging techniques, for example, first pass MRI, relaxometry, diffusion imaging, and so on. With that, I would like to thank my funding, my research lab at USC, and my employer, Canon Medical System USA, for supporting my work. And I would like to thank so much for your attention.